The year is 2157. Dr. Elena Vasquez stands before the largest telescope humanity has ever built, floating in the darkness beyond Pluto's orbit. Her weathered hands tremble not from age, but from the weight of what she's about to witness. Tonight, for the first time in human history, she will watch a quasar die. Not the violent, explosive death we might imagine, but something far more haunting. A slow fade into cosmic darkness, as if the universe itself were holding its breath and forgetting to exhale. The quasar she observes tonight, catalogued as J2157-3602, has been blazing across 13 billion years of space and time to reach her instruments. When its light first began this impossible journey, the universe was young, wild, and radiant with possibilities we can barely comprehend today. But now, as Dr. Vasquez adjusts the final parameters of her observation, she realizes she may be witnessing something profound. The end of the universe's most brilliant chapter, and perhaps the beginning of its longest, darkest night. This moment, suspended between past and future, between light and shadow, forces us to confront a question that has haunted cosmologists for decades. Are we living in the universe's brightest hour? Or have we already missed it, arriving fashionably late to a cosmic party that peaked billions of years before Earth even existed? To answer this question, we must journey backward through time to an era when the cosmos was not the serene, star-dotted expanse we know today, but a violent, luminous arena where matter and energy danced in ways that would reshape the very fabric of reality. Imagine, if you will, the universe at 1 billion years old. It's a teenager by cosmic standards, awkward and energetic, still figuring out its identity. Galaxies are smaller, denser, more chaotic than the elegant spirals and ellipticals we observe today. But scattered throughout this young cosmos are beacons of unimaginable power. Quasars, the most luminous objects the universe has ever produced. A single quasar outshines entire galaxies containing hundreds of billions of stars. They are cosmic lighthouses, so bright they can be seen across the observable universe, their light traveling for over 13 billion years to reach our modern telescopes. Yet despite their incredible brilliance, quasars are remarkably simple in concept. They are supermassive black holes feeding voraciously on the matter around them, converting mass into energy with an efficiency that makes our sun look like a dying candle. The story of how we discovered these cosmic giants begins not with advanced space telescopes or sophisticated computer simulations, but with a mystery that puzzled astronomers for decades. In 1963, astronomer Martin Schmidt was studying radio sources that appeared as ordinary blue stars in optical telescopes. But when he analyzed their spectra, the patterns of light they emitted, he found something impossible. These objects were moving away from us at tremendous speeds, sometimes approaching 20% the speed of light. Schmidt realized these were not stars at all, but objects so distant that their light had been stretched by the expansion of the universe itself, shifting toward the red end of the spectrum. The implications were staggering. For these objects to be visible across such vast distances, they had to be producing energy at rates that challenged everything astronomers thought they knew about the universe. The name, quasar, emerged from this discovery, quasi-stellar radio source. But as our understanding deepened, we realized we were looking at something far more fundamental than just bright radio sources. We were seeing the universe in its infancy, powered by gravitational forces that could tear apart stars and accelerate matter to speeds approaching light itself. Modern telescopes have revealed the true nature of these cosmic beacons. At the heart of every quasar lies a supermassive black hole, millions or billions of times more massive than our sun. These black holes are surrounded by accretion disks, swirling torrents of superheated matter spiraling inexorably toward the event horizon. As this matter falls inward, gravitational forces compress and heat it to temperatures exceeding millions of degrees, causing it to emit radiation across the entire electromagnetic spectrum. The jets of energy that shoot from the poles of these feeding black holes can extend for millions of light years, carving channels through the cosmic web and influencing galaxy formation across vast regions of space. These jets move at speeds so close to light that they seem to violate the normal flow of time itself, creating illusions where matter appears to move faster than physically possible. But here's where our story takes a melancholic turn. The golden age of quasars, that epoch of cosmic brilliance when the universe blazed with the light of billions of these cosmic furnaces, is over. It ended roughly 10 billion years ago, when the universe was only a quarter of its current age. The quasars we observe today are like echoes from a more violent, more energetic past, their light stretched and dimmed by billions of years of cosmic expansion. Why did this happen? The answer lies in the very success of the quasars themselves. In the early universe, gas was more abundant, and galaxies were closer together. Supermassive black holes had plenty of fuel to sustain their violent feeding, and their brilliant light could be sustained for hundreds of millions of years. But as the universe expanded and evolved, several things changed that would eventually starve these cosmic giants into dormancy. First, the expansion of space itself began to stretch the distances between galaxies, making collisions and interactions less common. Second, the first generation of stars began to inject heavy elements into the cosmos, changing the behavior of gas clouds and making them less likely to fall directly into black holes. Most importantly, the quasars themselves began to regulate their own food supply through a process astronomers call feedback. The intense radiation and jets produced by active supermassive black holes began to push gas away from galaxies, preventing new material from falling into the central black hole. It was a cosmic case of success breeding its own destruction. The brighter a quasar became, the more effectively it prevented future feeding, eventually starving itself into the relatively quiet state we observe in most galaxies today, including our own Milky Way. This raises a profound question about cosmic timing. When we look at the night sky and marvel at its beauty, are we seeing the universe in decline? Have we missed the cosmic equivalent of a golden age, arriving only in time to witness its fading afterglow? The evidence suggests that yes, we are living in a universe past its prime, at least in terms of raw luminosity and star formation. The rate at which new stars are born has been declining for billions of years. The number of active quasars has plummeted by orders of magnitude since their peak roughly 11 billion years ago. Even the process of galaxy formation has slowed dramatically as the expansion of space wins its battle against gravity on the largest scales. But this cosmic decline is not uniform or simple. It's more like watching a great city slowly empty as its inhabitants move to the suburbs, leaving behind magnificent but gradually crumbling monuments to a more vibrant past. The supermassive black holes that once powered quasars are still there, lurking at the centers of galaxies like sleeping giants. They occasionally stir when a star wanders too close or when two galaxies collide, producing brief flares of activity that remind us of their violent potential. Our own galaxy's central black hole, Sagittarius A star, is one of these dormant giants. 4 million times more massive than the Sun, it sits quietly at the Milky Way's heart, occasionally flickering with activity when it captures and devours small amounts of nearby material. But compared to its quasar cousins from the universe's youth, Sagittarius A star is essentially asleep, producing only a whisper of the energy that once characterized its kind. The Event Horizon Telescope's historic first image of a black hole, captured in the galaxy MADI 7, shows us one of these sleeping giants in a relatively active state. The supermassive black hole at MADI 7's center is still producing jets of material that extend for thousands of light years. But even this impressive display pales in comparison to the quasar activity that once defined cosmic luminosity. As we peer deeper into space with increasingly sophisticated instruments like the James Webb Space Telescope, we're essentially looking backward through time, witnessing the universe's brighter past. The most distant quasars we can observe existed when the universe was less than 1 billion years old, during the cosmic dawn, when the first supermassive black holes were forming and beginning their billion-year feast. These observations reveal a universe that was not just brighter, but fundamentally different from the one we inhabit today. Gas moved more freely between galaxies. Star formation rates were 10 times higher than they are now. The cosmic web of dark matter was denser and more dynamic, creating the conditions necessary for rapid black hole growth and intense quasar activity. But the decline of quasars is only one part of a larger cosmic story of gradual dimming. Star formation itself has been decreasing for billions of years, following a pattern that astronomers call cosmic downsizing. The massive bright stars that dominated the early universe live fast and die young, while the smaller, dimmer stars that form today can burn steadily for trillions of years. This shift in stellar demographics means that while the universe is producing fewer photons per unit time than it did in the past, the stars that are forming now will continue shining long after their more massive cousins have exhausted their nuclear fuel and collapsed into black holes or neutron stars. In a sense, the universe is trading spectacular brightness for longevity, choosing a dimmer but more sustainable future. The implications of this cosmic evolution extend far beyond academic curiosity. They shape our understanding of where we fit in the universe's timeline and what the future holds for cosmic evolution. If we are indeed living in the aftermath of the universe's brightest era, then we are witnesses to a unique phase of cosmic history. The long, gradual transition from the violent, luminous youth of the cosmos to its quiet, mature old age. This transition is not happening uniformly throughout the universe. In regions where galaxies are still colliding and merging, we can witness brief resurrections of quasar activity, like the anticipated collision between the Milky Way and Andromeda galaxies in roughly 4 billion years. Such events can temporarily awaken dormant supermassive black holes, creating new active galactic nuclei that briefly recapture some of the universe's lost luminosity. But these revivals are temporary and increasingly rare. The expansion of space ensures that galaxy collisions will become less common over time, and the supply of gas available to fuel supermassive black holes continues to diminish. The universe is settling into a new equilibrium, one characterized by slower change and dimmer skies. From our vantage point in this cosmic transition, we have a unique perspective on both the universe's glorious past and its more subdued future. The light from ancient quasars allows us to study conditions that existed when the universe was radically different from today, while our theoretical understanding of cosmic evolution provides glimpses of what lies ahead in the far future. Computer simulations of cosmic evolution paint a picture of continued dimming over astronomical timescales. In 100 billion years, the observable universe will appear much emptier as the accelerating expansion of space carries distant galaxies beyond our cosmic horizon. The cosmic microwave background, that faint afterglow of the Big Bang, will be stretched to wavelengths so long that it becomes undetectable. Future astronomers in such a universe might have no evidence that a Big Bang ever occurred, living in what cosmologist Brian Greene calls the island universe. But even in this distant future, traces of the universe's bright past will linger. The supermassive black holes that once powered quasars will remain, slowly evaporating through Hawking radiation over timescales that dwarf the current age of the universe. These black holes are like fossil remnants of the quasar epoch, preserving in their very existence evidence of the universe's more energetic past. The story of cosmic brightness is also intimately connected to the story of complexity and life. The heavy elements necessary for planets and biology were forged in the nuclear furnaces of the first generation of stars, many of which lived and died during the peak of quasar activity. The energy from active galactic nuclei may have played a crucial role in regulating star formation and galaxy evolution, creating the conditions necessary for the emergence of stable planetary systems. From this perspective, we are not just witnesses to the universe's declining luminosity, but products of it. The very processes that dimmed the cosmic sky also created the elements from which we are made and established the galactic environments in which life could eventually emerge. We exist in the sweet spot of cosmic history, late enough for stable planetary systems to form, but early enough to still observe the light from the universe's youth. This temporal positioning gives us an almost archaeological relationship with the cosmos. When we observe distant quasars, we are like future humans discovering the ruins of ancient civilizations, trying to understand a more dynamic and energetic past through the fading evidence that reaches us across billions of years. The James Webb Space Telescope functions as our cosmic time machine, allowing us to witness stellar nurseries and galactic collisions that occurred when the universe was a fraction of its current age. The decline of cosmic luminosity also raises profound questions about the nature of time itself in cosmic evolution. From our human perspective, the universe appears stable and unchanging on timescales relevant to our lives. But when we expand our temporal perspective to cosmic scales, we see that the universe is in constant flux, gradually evolving from one phase to another. The quasar epoch represents just one chapter in this cosmic evolution, preceded by the era of the first stars and followed by the current age of mature galaxies. Each epoch has its own characteristic timescales, energy sources, and dominant physical processes. We happen to live during the transition between the age of stellar formation, and whatever comes next in cosmic evolution. Understanding this cosmic timeline also helps us appreciate the rarity and preciousness of the current epoch. While we may have missed the universe's brightest hour, we are living during what might be called its most complex period. Galaxies have had time to develop intricate structures, planetary systems have had billions of years to evolve, and the chemical complexity necessary for life has had time to emerge and spread throughout the cosmos. In this sense, the decline of quasar activity is not simply a story of loss, but also one of transformation. The universe has traded raw power for subtlety, brilliant simplicity for complex beauty. The energy that once blazed from supermassive black holes is now distributed among billions of stars, creating the gentle illumination that makes life possible on countless worlds. The future of cosmic luminosity remains an active area of research, with several competing scenarios for how the universe's brightness will continue to evolve. Some models suggest that we are approaching a minimum in cosmic luminosity, after which star formation rates might temporarily increase as the last reservoirs of gas collapse into galaxies. Others predict a monotonic decline toward an increasingly dark and empty universe. Recent observations from space-based telescopes have revealed that the universe's expansion is accelerating, driven by the mysterious dark energy that makes up roughly 70% of the cosmos. This acceleration will eventually prevent new galaxy formation and may even tear apart existing galactic structures, hastening the universe's transition toward darkness. Yet even in the face of this cosmic decline, new sources of light and energy continue to emerge. The collision of neutron stars creates brief but incredibly bright kilonovae that can outshine entire galaxies for weeks or months. White dwarf stars in binary systems occasionally explode as type Ia supernovae, creating standardized candles that help us measure cosmic distances. Brown dwarfs, those failed stars that were once thought to contribute little to cosmic luminosity, are now known to be surprisingly common and may represent a significant reservoir of dim but long-lived light sources. The search for extraterrestrial intelligence also adds another dimension to our understanding of cosmic brightness. If technological civilizations are common in the universe, they might eventually create artificial sources of energy that could rival or exceed the luminosity of natural astrophysical processes. Megastructures like Dyson spheres or Sh-Kadov thrusters could harness the energy of entire stars, potentially creating new forms of cosmic luminosity that we have not yet imagined. But such speculative possibilities remain far in the future, if they exist at all. For now, we are left with the humbling realization that we are living in a universe past its luminous peak, witnesses to a slow but inexorable cosmic sunset. The quasars that once blazed across billions of light years are now mostly dormant, their supermassive black holes quietly waiting for the rare gravitational disturbances that might temporarily awaken them from their slumber. This cosmic perspective transforms our understanding of night and day, of light and darkness, on both terrestrial and universal scales. When we look up at the night sky, we are not just seeing the current state of the universe, but a temporal palimpsest where light from different epochs mingles in our telescopes and eyes. The most distant quasars we observe existed when the universe was young and bright, while the nearest stars represent the current, dimmer phase of cosmic evolution. Dr. Elena Vasquez, still standing at her telescope in the cold darkness beyond Pluto, begins to understand the profound implications of what she is witnessing. The death of quasar J2157-3602 is not just the end of one cosmic lighthouse, but a symbol of the universe's ongoing transformation from light to darkness, from chaos to order, from violence to quiet dignity. As she records the final photons from this ancient beacon, she realizes that her observation is itself a kind of cosmic archaeology, preserving the memory of an epoch that will never return. The universe's brightest hour may be behind us, but in observing its fading light, we participate in a kind of cosmic remembrance, ensuring that the memory of that brilliant past lives on in the consciousness that evolved during the universe's quieter present. The quasar's light fades to nothing, leaving only the gentle glow of nearby stars and the faint cosmic microwave background that permeates all of space. In the silence that follows, Dr. Vasquez contemplates the profound beauty of a universe that burns bright and fades away, creating in its dying light the very conditions necessary for observers like herself to witness and remember its former glory. This is perhaps the most poignant aspect of cosmic evolution, the universe's capacity to create, through its own decline, the intelligence necessary to understand and appreciate what it once was. We are not just witnesses to cosmic history, but its living memory, carrying forward the light of ancient quasars in our minds and instruments, ensuring that the universe's bright past continues to illuminate its darker future. In the end, the question of whether we are living in the universe's brightest hour reveals itself to be less important than the recognition that we are living in its most aware hour, when for the first time in cosmic history, matter has organized itself into forms capable of contemplating the very nature of time, light, and existence itself. We may have missed the universe's luminous peak, but we have arrived just in time to understand what we have missed, and perhaps, in that understanding, to find a different kind of brightness that will persist long after the last quasar has faded into darkness. The cosmos continues its slow dance toward night, but in the brief flicker of consciousness that has emerged on countless worlds, the universe has found a way to know itself, to remember its youth, and to face its inevitable darkness with the quiet dignity of understanding. In this awareness, we discover that the universe's true brightness lies not in the violent luminosity of ancient quasars, but in the gentle glow of comprehension that illuminates the darkness of cosmic ignorance, ensuring that even as the physical universe fades, its meaning endures in the minds capable of grasping its profound and melancholic beauty.